I'm visible and the presentation is visible. You see? Oh, you don't have the.
Yeah, because it's more.
So this was my idea, but this came too late. No, that the background should be dark.
Yeah.
Because it cannot be light, then you don't see anything.
That may, yeah, I think that's possible. I'm thinking to focus on one of the sides.
Do you have
no, the remote control. Let me check.
You're going to run for it? You run for the remote, and the girls are going for water, I think. I don't know. So they all leave us, Umberto. That's it.
Yeah, we are without net now. Safety net are.
It's okay, like in room A, it's completely depressing.
Delicious. You looked way younger before COVID.
Yeah, you see how bad is COVID, no?
Yeah.
What it does to you. I don't know, I have the other way around. It says this COVID is far more efficient to lose weight than running 3 times a week on the beach.
Yeah.
So Felipe is trying to get the zoomer in, then we can play around a little bit with. That was too late to tell you, Pam, that actually, if the background is white, what they said, you don't see anything online. So perhaps this works. I don't know yet.
We'll wait a couple more minutes, otherwise we will have to start. Not to delay.
Yeah, because we have very interesting talks today. Panos is here.
Morning.
Good morning, Pablo. Did you wash your t-shirt? Huh? No, distance. Did you wash your t-shirt?
It's fresh, it's fresh.
It's fresh. Just from the line. You can see the pizzas. Sorry, guys. We don't have. We don't have. Oh, that's. Okay. I saw another lot of people trading. Okay, good. So we start, guys, or
Yeah, let's start.
we start now. Boom. Oh, you do that now.
Yeah. So thank you all for coming to the last session of COA. And it's an immense pleasure to have in presence Elysius, our host, and you will deliver the first talk called On Computational Procedures for Optimizing an Omnichannel Inventory Control Model. Go ahead, Elysius.
So good morning, everybody. What's clear is that I wanted to do an experiment where we have a dark background. What you see on the picture there is 2 persons, one 20 years ago and the other one is nowadays, let's say, both have hair, okay? So I've been talking about inventory control a lot also during ICCSA, so it gave you some idea. Last year, this boy was doing an inventory control model where he said computationally it takes him days to compute something, okay? But this is the moment that blows my interest because I've been working on this for a long time. Okay, so inventory control. I give you a picture. This other strange word, omni-channel, that looks very, very difficult. Basically, it means distance. Basically, it means that you have more channels. That means that you sell in a shop and the same product you sell online. It's a difficult word for that. Why is there a challenge over there? If I want to take into account the current inventory I have to assign part of the inventory to the shop and part of the inventory to the warehouse. That's what the story goes about. Okay. So first, what I will try to do is I will get you in the mood again of inventory control. And the first thing I want to talk about is demand. We have a certain inventory control model, which is used a lot, which is called economic order quantity, that actually assumes a little bit that the demand is continuous over time. So your inventory is decreasing linearly, okay? So that's the linear line you see in the time. On the x-axis, you see the time. On the y-axis, you see the demand. There are models for variable demands, and mostly I've been working on stochastic demand. Interest me. You also have been work on non-stationary stochastic demand, but even in 2012 in ICCSA, I gave a talk about that. Now I want you to think Poisson. So what's Poisson say? The Poisson model says something that man walks into your shop, buys the electric scooter, okay? Other man walks into the shop, buys the scooter. 2 hours later, boy walks into the shop and buys the scooter, okay? This is a so-called negative exponential until arrival time. That means you sell on average 3, 4, 5 of these things a day, okay? But it follows a so-called Poisson distribution, no? I want in your head the following picture. On the x-axis, you see the time. On the y-axis, you see the amount of cans of beer in your fridge, okay? The cans of beer are going down. The number of cans of beer is going down. This is randomly because it depends on how fast you drink and whether friends are coming, this type of stuff. One of the inventory control rules, which is called policies, says at a certain level, you run to the shop, to the Lidl, let's say it over here, and you buy always 12 cans. 24 cans or 10 cans, I don't know. That number is called Q, okay? Your order quantity. At the other level, where you decide when you run to the shop, is called a reorder point, okay? This is an example of a policy, right? There exist several policies. I give you this picture now. Now on the x-axis, I put the inventory level. On the y-axis, I tell you how much to order. So my story is basically that the green line gives this SQ policy that says if you have enough beer, don't go to the shop. If I don't have enough beer anymore, run to the shop, okay? The cost I have is the inventory cost to store this and the cost to run to the shop. Now, as you're going by bike, it's not very expensive, of course. Another model is called the SS model, where S stands for order up to level. And I wanted you to see this number that Scarf in 1960, he said that for some models, of course, this policy is optimal, okay? What is this policy? So at the same S level, you run to the shop, but you don't always buy the same number. You buy up to a certain level. You take care that you have 40 cans of beer in your fridge after you went to the shop. That's a little bit the model, okay? How could this Scarf have discovered that this might be optimal? Probably, I'm certain about it actually, because, okay, there's the article. We used nice integrals and this type of stuff, okay? Nowadays, I think what my students get very much in the fingers is that they would do a simulation, or at least Philippe would do that, with the multi-agent models. You would do a simulation model, what's going on, and then you adapt your, like actually what happens over here, now in this picture. You simulate it, you change a little bit the S level and the Q level, and based on that, you take the one which is best. No, at the moment I'm in integer program, so could be handled. No. Now the most beautiful thing is, of course, to do dynamic program by Bellman 1958. Okay, that's very beautiful. Now I'm always tempted to tell the theory about it, but okay, I will try to forget the theory, and we are in computational science now over here, and tell you a bit of what this means computationally. Okay, Computationally, I try to depict in this way. First of all, for each stage in this moment, for each state at this moment, I see that as the inventory I have in my fridge. I'm going to give an evaluation. If I have a lot of beer, very good. If I have not a lot of beer, less good. Now this evaluation I put in an array called in computational science. No, mathematicians would call it vector. Okay, so you put it over here. Now the procedure I'm following is that backwards I'm doing two things. Namely, I take a decision. Okay, I start with 3 cans of beer. My question is what to do. Hopeless, of course. How can you survive with 3 cans of beer when your friends might come? Okay, so I have to take a decision first. Or let's say it like that. And after that, I have a realization of demand. And then I know where I enter. And that's actually the thing I'm going to minimize in cost or maximize. In this case, I did something wrong. No, I said minimum. With expected sales, I'm going to maximize that. Okay? The Q that comes out of this, the arg max, let's say it like that, that's the optimal policy for this level. Okay? Not directly. I have to repeat this. What is repeat? You take this array V after you calculate, put it over here, and repeat. Up to convergence. So what this convergence means, that's the nice theoretical part. I shouldn't go into there. But it means actually that if I subtract this V, W from the V, or the V from W, it goes to a constant. So there's no difference anymore. It's also called a span. Okay? Oh, to check a little bit, we made an example some years ago. We put it in a small paper to explain to the world with certain cost function. I'm doing cost here now, but I can't remember. Okay. The computational thing is over here. So actually, computationally, we are talking about do loop. Okay? So I have a big do loop based on I copy V and the W. I have a do loop that says for each state I have to do something. I have a do loop that says I have to evaluate my decision, and I have the events. Now, what I found in the cooperation with this young guy actually is that he did things much better than I did before, in the sense that this box that you see over here, he put it in a matrix. Why is this much better? So instead of doing this do loop that I'm doing over here, you can replace this do loop by a matrix multiplication. And why is this nice, Pablito? This is nice because if you're doing MATLAB or we are doing this, in this case, we were in Python, if you're doing do loops, it's hopeless. Okay, so you want to use codes, predefined code, which is much faster. Okay. So I learned something of this guy. Now, an example of an outcome is this. Okay, I have the inventory level here, and this was the optimal order quantity, and this was a surprise because we thought that if you have 0, it should be 10 or 11, not 9. Okay, how do you know it's not optimal? Right. You take this guy, you simulate it with the model of Philippe, and you'll find out cost. 9 is cheaper than 10. Okay. That's fun. Good. So this is a bit the idea of the value iteration I'm sketching now. Now I wanted to give you a feeling of what's the headache that's coming up. The headache is coming up because the state space is going to be bigger. This is why in the past they said this dynamic programming is not feasible. And we wanted to show it's feasible for the things we were studying. So this is an example where I have old and fresh distinguished, and I want an optimal policy. That means that in this picture that now I'm in two-dimensional space. I'm still doing the same. The only thing is that the number of states is increased. Okay, so the complexity goes up with the dimension. That's a little bit. But what also happens is that the bounding of the state space, I mean, the maximum inventory you can reach has to be bounded very well. And I learned that from this type of picture. So what this picture shows, for instance, is the old level and the new level. and this gives the amount I'm going to order. Okay. After I do my exercise, I know I'm never going to order more than 3 units in this example. This is extremely interesting because that means that your inventory will neither be very big, never bigger than 6, for instance, no? Theoretically. Okay, this is another picture which measures after I do the simulation, or I do a very elegant eigenvalue 1 Markov decision thingy. Did it in that paper. But it always has some surprising things, no? Because you see here that this never occurs. You never reach 0, it says. So that was funny. Now you go to the model of my friend, okay? The first challenge we took from literature. So in the problem of my friend, I do not only decide the order quantity, I also decide how much I put in the shop at the beginning of the day, okay? That's actually the green dot you see over here, okay? The blue dot is how much, this is the inventory level. The blue dot tells me how much I'm going to order. Now, how much I'm going to order apparently is, for this model, is the SS model. You also see that what I'm going to put in the shop is limited. Why? Because there will never be infinite demand in the Poisson distribution I have over here, and it costs something to put it in the shop. Okay. So over here, I also learned from him that we could do this trick with the matrix. Okay. Yeah, to replace actually this do looks by a matrix vector or matrix array multiplication. Okay. And what you observe over here is we are in computational science. We are very intrigued by how far can we go. So you see the computational time going in. Now the well-known pictures of Leo over here. Okay. And before last slide, sorry, we are very safe, Umberto. What we wanted to know actually, first of all, was what was written already in the 80s, that this is not very tractable for lead time. Lead time means I have to not only to keep track of how much I have in store, but also how much I ordered yesterday, day before yesterday, 3 days ago. Okay. So my state space is exploding. That's what I wanted to do with this picture. Actually, so I have pipeline inventory coming up because I ordered some day ago. Okay, it's in 2-dimensional space. We also like this picture that follows from the simulation I'm doing. Okay, the blue dots, or the green line is the inventory line. Not really a line now, because it should be a histogram type of stuff. But the blue dots are the amount I'm going to order. This follows from the simulation. No? Okay. Now the good news is that this is the last slide, so far so good. Yes, I hit many things in the same slide. That's always bad for the message, no? The real question we had was not so much about the lead time, it was the question about if we sell online, then we have to keep track how much we sold. Why? Because guys are going to return, have the right to return to the shop. Okay? How much is going to be returned? So the complexity, actually the complexity doesn't increase, Anna Christina, but we just take more events, okay? With a binomial distribution. Okay, that makes the state space bigger. That's a bit what we sketched in the paper. No, I should shut up basically. No, given the amount of noise I'm making. So the picture, the basic picture in the paper is about the complexity that goes up and how much we can handle in the size of the problem. Okay. Repeating, this was a Python implementation with all the clever things we could invent. And our question was actually, how big can we make now? So you see that the number of states don't like this word, but okay. With the dimension, the number of states increases. The computational time goes more or less linear in there. So I think, okay, because the rest of the procedure is basically the same. If I do this pre-processing, I make this beautiful matrices, okay? So I stop over here before I start to explode, no?
Thank you, Elysius. Any questions, comments?
Do you try to use approximate dynamic modeling? I never used it, but I was reviewing once the book by Golden Power.
That's right. It's an old idea, no? But actually I used it in reservoir management of rest. It has to do with, okay, these were small examples parts. This was like 6 states. The dimension is like 6. 46, I believe, the inventory. What we do in the big models is I used interpolation for continuous storage, no? But in reservoir management, we were dealing with that because we have big state spaces. So basically what you're doing is that you approximate and then you adapt the state space and do the same thing again. It's intriguing. This dynamic programming, Panos, takes a lot of time in the implementation of this type of thing. We are not running a standard solver or something like that, the beautiful neons. So you have to put a lot of time in the implementation. But I was intrigued by this. Thanks. More questions?
Any further questions, comments?
Just really don't know with this kind of problems, but do you have a security level of stock for this kind of problems? Something zero or always?
No, we are not. It's implicitly in there. No, it tries to avoid to get out of stock. If you're out of stock, you're losing money.
Yes, don't have figures at the
Exactly. In this model, this type of models, it's profit oriented. So you want to have inventory. If the inventory costs are not high, of course, you want to have inventory to sell. If you're out of inventory, you lost the sales.
I understand.
But I did a lot of this service level type of thing. It's another type. That's also why I had the minimization up there. I think I did a lot of minimization. Whereas in this type of models, we maximize, and because you maximize, you want to gain money, that's principle. Exactly. You want to gain money, then you try not to be out of stock.
Any further questions? Thank you again, Elysius.
So you don't have to ask questions.
Our next presenter is Philippe, and he's going to present an external climate data extraction using foreign feature selection method in the context of occupational safety. Go ahead.
Do you want this?
Yes. Philippe, stay away from this area, okay?
Para cambiar. Just just uploaded. Ah, já está? Já. Ó, Filipe, quer que eu diga? Peraí. Vou só pôr a partilhar.
Hello, I'm Felipe Jimenez, and I will talk about external climate data extraction using forward feature selection method in the context of occupational safety. So I will talk about the introduction, methodology, results, and conclusion. This project is part of a big project in the Instituto Politécnico of Bragança. So we study the several studies try to explain, prevent, and reduce accidents today. So we are studying with other stars in Portugal how to reduce the problem that they have in the context of work. So several studies try to define measurements to contribute to reduce these accidents. So normally it's focused on data-led investigation to implement some preventive actions to reduce this. So these actions is like reduction of excessive workload, changing process and procedures, improving and involving machines and equipments, and providing information and training workshops. Some studies have discovered that exists variables that is non-specific for a place. So that is a global non-organization variables that may influence the occurrence of accidents. This happens with the climatic conditions. So for this case, don't exist yet a lot of works. So its few works and scarce strategies have been developed to explore these associations between the accidents and climatic conditions. So this work is an initial step to study these associations. So it's collected the historical climatic data and explore a method, automatic method for selection the relevant climatic features. So this work follows the steps: generating a data set that contains all the information about the climatic data, processing this data set to remove errors and changing some values to get better results. Feature select experiment to select the subsets and test the accuracy of these subsets, and the result, the final result, that is the selected features. For this study, it was necessary to study specific ways to collect this information from websites or servers. So the main requirements that we search for open access to the data, previous years information, and detailed information like humidity, temperature, visibility, and others. So the first strategy that we look for is web scraping. So it's like a robot to constantly access the web page to select some information that is relevant and then save the results. And this is good for select information that is occurring now, like the weather for today, tomorrow, but isn't a good option when we are looking for something historical. So we studied the second approach too, that is API. So API asks for a server to collect the information and save the results. This is good for access external data. And in the future climatic data set, it's important to collect all these informations because will be linked with the data set of accidental occurrences. So this will study together to select the best features. To get this data was used the National Oceanic and Atmospheric Administration API that has the historical data for weather stations around the world. So the location was selected according to the stars that we are working to. So was the places Bragança, Gaia, Felgueiras, Matozinhos, Sobreda e Guimarães, all these in Portugal. And was developed a Python script to interact with this API. So this collection of data was automated. So was obtained 6 data sets, one for each location. All the data sets contains the information about date time. So each record is hour by hour. Air temperature, water temperature, wind direction, visibility, humidity, cloud cover, precipitation, air pressure, and wind speed. So each data set contains information from 2017 and 2021. So the pre-processing steps that we use was eliminated error of physical sensors because exist physical sensors that collect the information, and sometimes they has errors of writing or reading in the website. So the first step was eliminated these records, and after this was pre-processed the data information to generate day, month, hour, morning, night, dawn, afternoon, weekday, spring, summer, winter, and out. So in the total, 20 input features and one target was for each dataset. So when we has huge datasets with excess of features, then noise are addicted to the model when we try to predict. So this is called the curse of dimensionality, and this decreases the prediction success. So the selective feature is a technique to reduce the size of the subset, the inputs, choosing a subset with just the relevant features, resulting in a lower computational cost model and better interpretation data. So this is a problem that involves combinatorial because you can create a lot of subsets to test and select, and this permits to improve the machine learning algorithms. So to ensure that we are selecting the best features was used the forward feature selection using the grid search algorithm as search algorithm. Here I create an example to explain how this works. So this is the basic dataset, which has 3 features, F1, F2, and F3, and this is the target. So initially, we don't have any idea of how to start the process. So was separated each target as a model of prediction. So it's create a model with just one target, one feature, and try to predict the target. So this get this accuracy. So F1 get this accuracy, F2 get this, and this is the first iteration. After this first iteration is chosen the feature that have the best accuracy of all. So in this case is F1, and F1 is fixed to the next iteration. So F1 is here, and the other features are combined with F1 to generate new models. So F1 and F2 is used to generate a new model here with this accuracy, and F1 with F3. So this process repeats. In the final, we have feature order of importance. So F1 was the best feature selected, F2 was the second, F3 was the second, and F2 was the third importance. And in this case, we can see that the F1 plus F3 was the best solution that we found. So we can accept this as the best model that we can generate. All the possibilities in this case is H, but just test 6 subsets. So F3 plus F2 and 0 and empty group was ignorant. So this, in this case, isn't so relevant, but when we increase the number of features, that is a huge difference, because here we have a brute force example, so that's all the possibilities. It is have the optimization using the grid search. So the properties of this experiment was initial subset was choose features exempt. Air temperature information was used our target because another studies use and comproves that is important to accidents. And all the remaining features are used as input to the FFS, the feature forward selection method. So the information, the predicting model was used as linear regression algorithm provided by sklearn library in Python. And the dataset was split in 70% and 30%. This is how the schema of the tests occur. So for each data set, for each location, was repeated 100 times the test to compare if the results really are working and have a pattern. So it's tested 210 subset combinations, 2% of all combinations, and generate the model, calculate the mean square error and the accuracy for each size of the subset. And after this is the comparison. All the process takes 36 minutes, so 6 minutes approximately for each location. So this is the final result for each location. So here has 4 variables that was selected in all the locations. In this case, water temperature, dawn, night, and summer. Has some others that has specific locations to improve the model. And the final is that don't go to the final dataset, that is removed. Here is the graphic about the accuracy improvement by the size of subset. So in this case, we can see that there are limits of improvement. So the others don't have a relevant improvement after this. And was selected 6 variables for each location. So this has 6 for each location. And this is the mean square error for each size of subset. So this is the same thing, but it's a different measure. So collecting all this data was selected 9 variables. So cloud cover, humidity, visibility, water temperature, wind direction, night, dawn, winter, summer, because it's the average of all the locations. In the conclusion, in the scenario used, the forward feature selection approach proved to be advantageous because optimize the accuracy of predicting models, resulting in a good subset based on the accuracy of the model, naturally combines multiple features. These don't happens in correlation methods because it's directly tested with the target. And in this case, we group all together and test the prediction. So naturally combine multiple features, provide feedback of importance of each feature. And this is an automatic procedure, but these have some weakness, like the time compared to the person and others correlation methods, and the feature, when the feature is elevated, also increase the time. And the FFS is not deterministic because use 70% of the data set in 32 tests, and this can change the final results. So about the climate data set, has different characteristics for each location. So applying the method, we can have different or specific subsets for each location for maximize the accuracy. And from 20 features, who are just 9 selected as final, and 4 features for all, was chosen for all the localities. So this indicates that these features can have importance in general context instead the specific locations. So how feature works is to create new data sets to join this study. So holiday with national and regional, and the events, regional events for each of these locations, and use the FFS to select the best features with all this information to detect if it exists correlation between these factors. So discover the features that is more important and generate the final model to predict these accidents. So it's important to future work to test the FFS method with different approaches to try to improve the time consuming and combine with statistical methods. And that is all.
Any questions? I only have one quick question. You use forward selection. Why not backwards? Starting with all 20 and going back.
I tested 2 approaches, and the time consuming of the backward was elevated compared to this, and I don't get a good accuracy in the final result. So I believe this method fits better in our case, but the 2 approach was best.
Okay, thank you. Let's thank again. I will be the next presenter. So the subject of this presentation is how life transitions influence people's use of the internet, and I will try to emphasize the clustering approach. This is a large study, and this is only a small part. It's a joint work with Bologna University and Coimbra University.
Try to stay close to the mic.
And
Microphone is very cool.
oh, okay. And I will speak louder. And the outline is the following. I'll start by a very brief introduction. Then I'll explain how data was collected, the sample, the measures used. And I will focus on clustering and data analysis. I will show some interesting results, not so interesting results, and the conclusions. So nowadays, internet is important for all of us, and internet can be either a problematic issue if instead of paying attention to this presentation, you are looking to the computer or cell phone or so on. but can also be a functional tool if you are looking to the computer and looking to what co-authors do and stuff like that. And every day we use internet in both ways, in functional and in problematic way. Here, the goal of this research is to understand how internet and in particular social networks can influence these behaviors, these two behaviors, considering a particular feature, which is life transitions. Typically, life transitions occur in young adulthood. So that's the main age we are trying to focus. The goal is to define user profiles, not a priori, because typically user profiles are defined a priori, but trying to search for user profiles that emerge from the collected data. The main advantage of this approach is that the data will give us this information instead of us giving information to the data. So this is a very nice diagram that is a summary of the theoretical part that I do not fully understand because it's mostly psychological stuff. I just know that we want to understand the interaction between potential resources of the internet and potential challenges, and the main focus is in the middle. So it's in the transition, and transition is changing school, finding job, moving in another city, moving from one place to another, and so on. And this theoretical part gives origin to a very nice model, and we will try to assess this model through a cross-sectional study that collect data for all the variables embedded in that model. And it was an online questionnaire that was delivered in Italy, online questionnaire, and it was a very responsible questionnaire, like most questionnaires are nowadays, and it has to go through several stages, and I will emphasize this because in the next slide there's something that I would like to stress. And there was a committee for questionnaires and so on. So it took a couple of years to deliver these questionnaires. The sample is quite large. It's 500, more than 1,500 participants, most females, and the mean age is young adults. The questionnaire items are grouped in three subsets, mainly the measures of problematic internet use, the measures of functional internet use, and the measures that I could understand better is the measures of the internet use habits. For me, that's the most interesting part. For the co-authors, the other two are the most interesting part. In order to do my job, to try to define user profiles from the data, I only focus on the last subset of measures or variables. There is a very, very large number of variables in this model and data collected, and we only select 15 variables, 3 continuous and 12 binary. And the continuous was age, the number of hours online, and the number of online contacts, and then the devices typically used, computer, tablet, smartphone, and then the applications used. And here I will stop a little bit because these type of studies become obsolete very quickly. And if you look to the social network, there are at least some that nowadays are already very used. Can you say something that it's missing there?
TikTok.
TikTok. So in 2 years, this study became obsolete. Why? Because that committee needs to approve and so on. And nowadays, in Portugal, it's the same everywhere. So we need to submit something to a committee that need to approve the questionnaire and so on. And TikTok is missing here. But nevertheless, the results still interesting. So based on these variables, we want to define user profiles. The most commonly used clustering approach is k-means. In this, using that type of data, it's not possible to use k-means because a cluster mean needs to be computed and makes no sense when we use categorical data. So the second most used approach is k-medoids, which is almost like k-means, but instead of cluster mean, we use a representative individual. So, and then we need to define a dissimilarity or a similarity measure, or simple. We need to define a distance measure, and we need to compute the optimal number of clusters. Okay, we use k-medoids, and it works basically like this. After defining the distance measure and the optimal number of clusters, we randomly assign k-medoids, and then we compute the initial clusters, and then we iteratively find the best clusters. The two main things for this algorithm to work are the definition of the dissimilarity measure or the distance measure and the optimal number of clusters. We use MATLAB algorithm for k-medoids, which is partitioning around medoids, and it works exactly like described. We have here an example for two clusters for k equal to 2. We initially assign randomly two representative elements to medoids, and then using a distance, we compute the initial clusters, and then we change the medoids and we recompute until counters. So it works like this, but we need to define a distance or a dissimilarity measure. And assuming that we have a matrix with our data, dissimilarity matrix is typically a symmetric matrix with zeros in the diagonal. 0 means that they are equal. A distance close to 0 means that they are similar, and away from 0 means that they are not alike. The most common distance used is the normal distance, the Euclidean distance. But in this case, it makes no sense because we are using categorical data. So there are many possible different distances. And one of the most used is the Mahalanobis distance, which is the sample covariance of our data matrix. So we use this distance. And the second thing we need to define is the optimal number of clusters. There are very fancy ways to do that, but the most simple way is just trying 2, 3, 4, and so on number of clusters, and then stop when the measure, the aggregate measure of distance between the elements doesn't improve significantly. And that occurs immediately for k equal to 3, and this is the first set of results, the ones that I like the most, but they are not the most relevant for this study. But that's the one I will show because I will also show the others. But these ones are, I think, more interesting. And we were able to define 3 user profiles, 3 different user profiles. Cluster 3 is the user profiles of the oldest persons. And we can see that it corresponds to the ones with less number of online contacts, but that interact mostly in work time, the oldest. And they mostly use computer and smartphone, and they like to use WhatsApp and email, mostly, which was interesting for me. And then we have the youngster cluster, or the youngster users, which is cluster 2. And in cluster 2, the youngsters, we see that the number of contacts online is the maximum, and they prefer to use computer and smartphone, and they like Facebook, YouTube, and WhatsApp. And then there was a third cluster, which is young adults, that use mostly computer and smartphone, and they also like Facebook and WhatsApp and email. Okay, so this was very interesting for me, but the co-authors was not very interested in these results. They were much more interested in the other two groups of variables, the goal of this study, which is functional use or problematic use of the internet. So to assess that, and for that clusters, we perform ANOVAs for all the remaining variables, and they were very pleased to see that for all variables except one, there were statistically significant differences between the three type of users for that variable. And there is a lot of theoretical explanation for that you can read in the paper. So I just can say that they were very pleased that the clusters find users that correspond to different profiles psychologically. So in conclusion, and we already know that internet can be either a functional tool or a not functional tool or a problematic tool, regardless of being in a transition phase or not. And we were able to, from the data, extract three types of users. And the most important of this study is that differences were identified between all dimensions measured, particularly between youngest and oldest users. And that's it. Thank you.
Can I ask? I saw.
If I know how to answer.
Yes. You had 1,000 and about
500, yeah, 1,500.
Respondents, and they are 60%
Female.
female.
Yes.
The age. Do you have maybe you have also a graph with
We have.
Is the female are the oldest one or the youngest one?
Well, the range, the age range, the mean was 31 years old, but the range was due to some ethical issues, it could only start after 18 years. The initial goal was pre-adolescent, so in the high school, in the 3 years, but we couldn't do that, so it only started with 18 years, and then it goes to 45 years. So, but it was a normal distribution.
Okay.
Actually, it was not. It was a distribution a little bit more for the right. So, because it was easier to collect data from college students. But still, 33 years old means that there's a lot of young adults also.
It's a very interesting.
Yeah. Actually, that's all credit for the Italian group because they collect all the data in Italy.
What's the standard deviation for female and adult, young adult?
I don't know by heart. I don't know. Yeah, it was somewhere there.
Again,
Can you?
Can check it.
You can check the paper. No, but it was in the third slide, I think. 30.
At the end of the
Yeah, I think.
no. We identify that young adults, someone being 34, and those standard deviation.
Oh, there. Wait, maybe up. Yeah. Yes. I cannot see. Go ahead.
The clusters join.
Is the
You join.
Yes, it's short.
Join.
Yeah. It's not 50-50, but Any further questions? Thank you again. And the last speaker is Ana Rocha. And
Sometimes it's
the floor is yours. No, you have 20 minutes. You are just in.
because we have the coffee break, some break, then to start.
You pay for the coffee break, we have to take off.
Yeah, we have to take coffee before finals. So thank you very much. I will present a bibliometric review and analysis of traffic light optimization. So this is a project about well-being in urban centers. And in the beginning of the project, we have to make a literature review about the theme. So we made a literature review about the traffic lights. So we are specifically working on optimizing the traffic lights cycle. So I will begin with the introduction, the methodology used here and the results, and finally to conclude this work. So there is a significant increase in the number of vehicles on the roads, and obviously it can cause travel delay, queues, the number of stops on the roads, they are increasing also, and increasing the gas emissions and so on. So it is fundamental to control the traffic light cycle in order to increase the efficiency of the traffic system. There are some studies that are looking for solutions to the problem of congestion of traffic, and they are specifically talk about the traffic lights and how to make the process of the vehicles safer and at low cost. So we want to optimize the transition phase or the shift between the signal timing plans, and we hope to result in the reduction of the traveling time, the stops, the delays, the reduction in the gas emissions, the fuel consumption, and so on. So we made some research questions, and that we want to answer with this bibliometric review in order to manage the traffic lights smartly, and the kind of data that has been used, and the benefits of this kind of work that has been doing. So this is the methodology used. So in step one, we have systematic mapping planning. So we formulate the research questions and select the databases and the resources. In step two, we conduct the search. Step three, we select and make the bibliometric analysis of the primary studies. And then we finally select the papers and study only that papers, only by this, by this approach. So in the formulation of the research questions, we formulated 3 questions. The first one is how the existing approaches, optimization techniques and simulation are used to manage the traffic lights smartly. The second research question is what kind of data? So we want to know if the data is used on offline or online. Obviously, we'll see the results in the end. And research question 3, how beneficial is it to propose an optimization approach to optimize the traffic system? In step 1, we select the Scopus and Web of Science databases, and the period of 10 years. So from January to 2012 and 2022. Then we select some keywords. They were traffic light, optimization, data, smart, or intelligent. We had to select some to use some exclusion and inclusion criteria. So the study should be written in English. These are the exclusions. So the studies that were not in English, we didn't use. Of course, we don't understand some of them, of course. The full text should be available. If the research does not cover the topic of smart cities, we don't use it. And the document type shouldn't be a conference paper, but should be an article, a review, or something. The inclusion. So the papers to be selected should include the reducing of traffic congestion and the delay time, and should look for road safety and traffic forecast topics. So after selecting the two, the Scopus and the Web of Science, so we took a total of papers were 157 papers were uploaded, and after removing the 66 from Web of Science, 69 from Scopus, but some of them were duplicated in both databases, and total of papers after the removal process were 93. So 66, 71% from Web of Science and 29% from Scopus. This is the kind of the type of documents that will be used. So the 93, most of them are articles, and this is a word cloud for the type of keyword that is used in the papers selected. So we can see here optimization, traffic congestion, intelligent transportation systems, are the traffic control, are the most important, the most used. These graphs, these diagrams, these figures shows the documents published per country and here. So we have the range of years that we used for the paper selected, and we can see here that the United States and China are the countries with the most studies published in the last 10 years. Here is like a zoom, but we see here the percentage of documents published in the last 2 years when compared to the average number of published papers, published documents in the last 10 years. So here we continue to see that the United States and China are the countries with the most studies in this area. Then we select some papers with the criteria used, and the total full papers analyzed, the result of the number of papers that should be analyzed is 39. So after analyzing these 39 papers, we finally have some answers to the questions. So regarding question 1, the existing approaches, we can say, so the question was, how are the existing approaches managing the traffic lights smartly? So the research question, this research question
raised that the existing approach to managing traffic lights smartly, and it was possible to find many approaches. 24 different technologies and algorithms are used in traffic lights optimization. Here is the identify strategies. So the algorithms, and lots of them, we know them. We are aware of this. Regarding question 2, what kind of data? So if they use offline data or online, 18 papers are from these 39. 18 papers are using offline data, and 21 use real-time data. Regarding question 3, so how beneficial is it to propose an optimization approach to the traffic system? 8 of the 39 papers presented answers to this question. So in general, the results confirm an increase in the overall performance of the system when we apply optimization approach in the traffic light system. But most of the papers do not quantitatively present the results, but only in a qualitative way. Here we can see some of the papers. So regarding the question 1, regarding the question 2 and the question 3. So here we have the methodology, the algorithm used. SUMO is a simulation of urban traffic that usually is the most used to combine with the optimization. So we must simulate how many the traffic. Here use particle swarm, for example, and offline data, and other algorithms here, and to see what kind of data we use, and the use and the improvements that the results they have. So usually they use optimization to reduce the delay time of the travel, the delay time of the vehicles, and sometimes not so usual, but also the gas emissions and the fuel consumption. So this is a research project that aims to improve the understanding of traffic light management when combined with optimization, and this is only a bibliometric literature review, analysis and bibliometric literature review. So, as I said, the United States and China were the countries that have most of the studies in the last 10 years. We select, after applying the methodology, we select 39 studies, 24 of them showing the existing technologies and algorithms, 18 papers using offline data, and 21 with real data. So that's all. Thank you.
Thank you, Anna. Any question? Lots of questions.
Maybe I missed the CPU, the citations of the paper, like the choice.
If I use?
Number of citations.
No. In fact, I didn't use. We only used the keywords of the paper, and if mostly the keywords. Yes.
And if I may ask did you encounter, I mean, something that is not a record, but did you encounter papers related to traffic light without lights? I mean, one of the, there is a report from the, about the 4.0 industrial revolution that speaks about cities without traffic lights, because the cars don't communicate with each other. And they were even saying that in 2030 we'll have the first city without traffic lights, because all the cars can communicate with each other, and this is decided automatically by loudly. You find anything around this?
In fact, we were not searching for that, but we're not searching for that. But this is a project with the communications and other areas, not only optimization, and other colleagues from groups of intelligence and so on. And we intend to use that idea. So traffic lights, we don't without traffic lights, but we will consider, yes, traffic without traffic lights, and we will consider that the cars, the vehicles will communicate, because we have some people that works in communications, and they are interested in simulating that using a simulation that they have already, and we will try to do that.
Maybe too soon to do that on cities, but you have small environments, for instance, companies, airports, and so on, that will start using this kind of technology because they control all the carbon. Sorry.
Even before using this without traffics, still today they use sensors. For example, buses, school buses, when they approach the traffic light, and then they go. So there's some kind of priority in certain vehicles.
Yes, yes, it's a good idea. Yes.
Maybe in the future.
Yes, the idea of Paula is very interesting, but it is, I don't think it is real in the near future.
Yeah.
But it is interesting. And the sensors also.
Sure, even many years ago, when you approach the traffic light, they sense a car and they keep it clean. It's much similar, but all civilized countries. Well, Sweden 30 years ago, I was.
I saw that the Spanish dictionary say very explain but difficult from based on that. Second part, we did a study about the but at the end you have to have reaction time. You have to have camera to see how many are there.
Very insane.
You have to have a table. I have 10, 12, whatever way I have 13, so I have to choose. You don't have to do it or average situation. But you have to happen opposite of this. Because the average way can be changed.
The beauty is to use dynamic programming.
Yes.
The first dimensionality.
But you already
Dynamic.
We have several papers for example on that, on traffic light control.
Yes, you have already said to me. Yes, we have to improve.
One more question, go ahead.
Yeah, question, yeah, thank you, great. Question problem for anyone. Yeah. In what circumstances the traffic light was introduced first time?
What?
What time it was introduced? For what purposes? Do you think it help from or really impose some distraction which create the problem for traffic?
You mean that without traffic lights, we would.
Yeah, that's the question you follow up. Which one you raised?
And even in Africa.
It depends on the country.
Exactly.
From our point of view, because I think look at structure. If structure is perfect, like biological structure, you don't need the traffic. You don't need the traffic to stop blood circulation or system or neuro for information for brain structure. So as long as my assumption, if the structure is really perfect, and probably the traffic lights tend to, disturbed.
As long as the
A lot of
brain,
people
as long as the brain is working well, we don't need this stuff. Conclusion.
Yeah, looks good, we don't need anything. Others?
I think it's a very provocative question to discuss over.
In the coffee break.
But if you want to close the session.
Okay. Thank you very much. We are closing the computational optimization applications workshop. Thank you all for being here in the last day and during the other days, and see you next year at Lesbos. Thank you.
Congratulations to the organizers.
Oh, thank you. We are organizers, you know. And to the organizers of the conference. Without the conference, we wouldn't have the workshop.
Foi interessante, toda a gente gostou.
Estás a ver? Às vezes.
Ok. Tu não vais ficar aqui, não? Vocês levam, vocês têm deixado de tocar as coisas. Eu tenho. Eu tenho. Olha, hoje já passou. Mas não dá para eu não vejo que a minha cheia de guardado com o também, já viste que uma câmera não está a ser feita. Também não viste eu também. Eu tinha uma câmera com
And so